Ever wondered how the internet travels at the speed of light? Let's dive into the mind-blowing world of fiber optic cables, how they're made, how they work, and why they power everything from Netflix to NASA. So, grab a snack, settle in, and let's dive into the hidden world of fiber optic manufacturing. Trust me, by the end of this, you'll never look at the internet the same way again. Let's start with a simple question. Have you ever wondered how your Netflix show streams in 4K, or how you can FaceTime someone halfway across the planet with barely any lag? It all comes down to these tiny, hair-thin strands of glass called fiber optics. They're the backbone of the internet, the arteries of our digital lives. And the crazy part? Each cable is thinner than a human hair, but it can carry terabytes of data per second, at nearly the speed of light. Fiber optic cables make modern life possible. They're the reason we can send emails instantly, back up huge files to the cloud, or video chat with friends across the world. Without them, the internet as we know it simply wouldn't exist. But how do you make something so precise, so flawless, that it can send light signals thousands of miles without losing information? That's what I'm about to show you. Believe it or not, the journey begins with sand. But not just any sand, this is ultra-pure quartz sand, with a silica content of over 99.9%. The reason for this insane purity? Even the tiniest impurity, like a speck of dust or a stray atom of metal, can scatter light or absorb it, messing up the signal. So manufacturers basically take sand and purify it at the molecular level, often turning it into silicon tetrachloride gas and then back into glass. It's like alchemy, but real. This purification process is so intense that the sand is essentially vaporized, chemically scrubbed, and then re-solidified into the purest glass you can imagine. The goal is to create a material that's as close to perfect as possible, because even the tiniest flaw can ruin miles of fiber. Next up is one of the coolest parts, creating the preform. Think of this as a giant glass rod, about the size of a baseball bat, that contains the exact structure of the fiber, core, cladding, everything. Here's how it works. They inject gases like silicon tetrachloride and germanium tetrachloride into a rotating glass tube. A burner moves along the tube, heating it up so the gases react and deposit a layer of pure glass soot on the inside. Layer by layer, this soot builds up into the core and cladding of the fiber. Then they heat the whole thing until it collapses into a solid rod, the preform. This all happens in a super sterile, clean room environment. We're talking NASA-level clean, because even a fingerprint can ruin the whole batch. The preform is like a blueprint for the fiber, containing the exact structure that will be stretched out into miles of cable. Now here's where things get really dramatic. The preform is hoisted up into a massive drawing tower, sometimes several stories tall. The bottom of the preform is heated to a ridiculous temperature, about 2,000 degrees Celsius, that's over 3,600 degrees Fahrenheit, until it starts to drip. Gravity and precision machinery take over, pulling the molten glass downwards and stretching it into a thread that's just 125 microns thick. For reference, that's barely thicker than a human hair. This process is mesmerizing to watch. The glass flows like honey, but it cools almost instantly, solidifying into a perfect ultra-thin strand. The speed and precision required here are mind-blowing. If the temperature or pull speed is even slightly off, the entire fiber can be ruined. Maintaining that perfect diameter is absolutely critical. If the fiber is even a few microns too thick or too thin, it won't transmit light efficiently. So they use lasers and sensors to monitor the diameter in real time, making micro adjustments on the fly. It's like glass blowing meets rocket science. The sensors are so sensitive they can detect changes smaller than a wavelength of light. Every millimeter of fiber is checked and double-checked because even the tiniest imperfection can cause signal loss or breakage down the line. Freshly drawn fiber is incredibly fragile. You could break it just by touching it. So the next step is to protect it with a special polymer coating. The fiber passes through a machine that coats it with a soft elastic layer. Sometimes a second harder coating is added for extra toughness. These coatings are instantly cured using UV light, so they harden without heating up the glass any further. This coating process is crucial. The polymer not only protects the fiber from physical damage, but it also shields it from moisture, chemicals, and other environmental hazards. Without this step, the fiber would never survive the journey from the factory to your home, or the decades it spends underground or underwater. Every single meter of fiber is inspected for defects. Lasers check for microcracks and cameras scan for surface imperfections. If they spot a problem, the process stops immediately. There's zero tolerance for flaws because even a tiny crack can ruin miles of cable. Some factories even use high-speed cameras and AI algorithms to catch defects that the human eye could never see. The goal is to create a product that's as close to perfect as possible because the stakes are so high. Now, a single fiber isn't enough for most applications, so they group fibers together, depending on what the cable will be used for. Ribbon cables line up fibers in flat ribbons, great for splicing lots of fibers at once. Loose tube cables bundle fibers loosely in protective tubes, which makes the cable more flexible and less prone to stress. Grouping fibers together allows manufacturers to create cables that can handle everything from a few phone lines to the entire internet backbone of a continent. To make sure the cables survive being pulled through pipes, buried underground, or even laid under the ocean, they add strength members like Kevlar, fiberglass, or steel rods. Buffer tubes and water-blocking gels help protect against moisture, vibration, and temperature swings. Kevlar, the same material used in bulletproof vests, is especially popular because it's incredibly strong and lightweight. These reinforcing elements ensure that the cable can withstand years of abuse without breaking or losing performance. Finally, the whole assembly is wrapped in a tough plastic jacket, usually polyethylene. For cables that go outdoors or underground, they might add extra layers like corrugated steel or aluminum to keep out rodents, water, and crushing forces. The outer jacket is the cable's first line of defense against the outside world. It protects the delicate fibers inside from everything from construction equipment to curious animals. Before any cable leaves the factory, it goes through a battery of tests. Optical loss and attenuation are checked to make sure the cable transmits light with minimal signal loss. Mechanical tests check for strength, flexibility, and resistance to bending or crushing. Environmental tests simulate years of exposure to heat, cold, moisture, and chemicals. These tests are brutal, but they're necessary. A single faulty cable can bring down an entire network, so manufacturers go above and beyond to make sure every product is up to standard. Once everything checks out, the finished cable is wound onto huge spools, sometimes miles of cable on a single reel. They're labeled, packed, and shipped off to become the backbone of the internet, phone networks, and more. It's kind of amazing to think that a single spool of cable would connect cities, countries, or even continents. At the heart of fiber optics is a physics trick called total internal reflection. Imagine a beam of light bouncing perfectly down a tiny glass tunnel, never escaping. That's exactly what happens. Light enters the fiber and hits the boundary between the core and the cladding at a shallow angle. Since the cladding has a slightly lower refractive index than the core, the light gets trapped inside, bouncing its way forward over incredibly long distances with almost no loss. It's like creating a light highway through a glass thread. Now let's break down the fiber itself. The core is a strand of ultra-pure glass designed to let light pass through without distortion. Surrounding that is the cladding, which reflects the light inward and keeps it from leaking out. There are two main types of fiber, single-mode and multi-mode. Single-mode fiber has a very thin core and allows light to travel in a straight line, ideal for long-distance, high-speed connections like undersea cables. Multi-mode fiber has a thicker core and allows multiple light paths, making it perfect for shorter distances like inside data centers or office buildings. So how does your data become light? It all starts with a transmitter. It takes an electrical signal like your voice on a call or the data from a website and converts it into a pulse of light using lasers or LEDs. That light shoots down the fiber at nearly 186,000 miles per second. At the other end, a receiver catches it and converts it back into an electrical signal your devices can use. It's light-speed communication, literally. Why do we use fiber optics instead of copper wires or wireless signals? First off, speed. Light moves way faster than electrons in copper. Then there's bandwidth. Fiber can carry way more data, often measured in terabytes per second. It's also immune to electromagnetic interference, making it much more stable. And let's not forget security. Tapping into a fiber line is extremely difficult without being detected. Plus, these cables are lightweight, flexible, and easier to manage than bulky copper. But here's the thing, making fiber optic cables is no walk in the park. The level of purity needed for the glass is almost unreal. Even a microscopic imperfection can ruin the signal. The diameter has to be flawless, and the entire process, from drawing the fiber to coating it and testing it, requires extreme precision. These cables have to last for decades, often in brutal conditions, underwater, underground, or even in space. Today, fiber optics are absolutely everywhere. They power the internet backbones that connect continents, support your daily Zoom calls, enable high-resolution medical imaging, and handle secure communications for defense and aerospace. Honestly, without fiber optics, the modern world wouldn't just slow down, it would come to a screeching halt. So next time you send a text, stream a video, or FaceTime someone across the world, remember, it's all thanks to these invisible threads of glass born from sand and forged in fire, crisscrossing the globe beneath our feet. The making of fiber optic cables is a story of human ingenuity, precision engineering, and relentless pursuit of perfection. From the purity of the quartz to the final spooling of miles of cable, every step is a dance of science and technology. And as our hunger for more data and faster speeds grows, these glass marvels will become even more important. So, what are your thoughts on this? Let us know your thoughts in the comments below. And don't forget to like and subscribe for more such content.